Let's have a look on the one component system. For a one component system, we're going to have a look on the phase diagram of water and phase diagram of carbon dioxide. Okay, so we understand one component system using the formula for degree of freedom. F equals to one component minus P plus 2. For the degree of freedom, it must be more than 0 or equals to 0, and phase must be more than 1 or equals to 1. For phase equals to 1, degree of freedom is 2. It is called bivariant. And phase equals to 2, degree of freedom equals to 1. It is called univariant. Whereby phase equals to 3, fundamental degree of freedom equals to 0. It is called invariant. We are going to look on these three variants in the phase diagram of water. In phase diagram of water, we have a graph pressure versus temperature. In this graph, there are three regions, as you can see: solid region, liquid region, and gas region. Each of the region, the degree of freedom is F equals to 2. It is bivariant. On the line, which is OA, AD, and AC, it is F equals to 1, which is univariant. At point A, which is triple point, it is F equals to 0, which is invariant or zero variant. We know that phase is a physically distinctive form of matter. So we have solid phase, liquid phase, and gas phase. These three phases can transform through a certain process. As the temperature increase, the solid can undergo sublimation to form gas, and from gas it's undergo deposition process to form solid back. How about the transformation between solid and liquid? For the solid, undergo melting process to form a liquid, and liquid will undergo freezing to form solid. Liquid will undergo vaporization to form gas, and gas will undergo condensation to form liquid. The solid has the greatest order, meaning that the particles are closely packed together and it has definite volume and shape. Liquid have definite volume but not having a definite shape, and gas, it has indefinite volume and shape. So gas has the least order. In phase rule, we are going to learn on phase diagram, and in phase diagram there are phase boundary. So what is phase diagram? It shows the region of pressure and temperature at which its various phases are thermodynamically stable. In phase diagram, there are phase boundary. So this phase boundary is a boundary between regions, shows the value of pressure and temperature at which two phases coexist in equilibrium. This is example of phase diagram. In this phase diagram, we can see that it summarizes the condition at which a substance exists as a solid, liquid, or gas. The phase diagram can be plotted by pressure versus temperature. From the phase diagram, you can see there are three phases involved here: solid, liquid, and gas. We know that a certain process, we can undergo certain process to transform solid to liquid or liquid to solid, and also liquid to gas or gas to solid, and also solid to gas or gas to solid. So this is phase boundary, and uh, on the line of the phase boundary, you can see here there are 2 points. So one is triple points and another one is called critical points. What does it mean by the triple points and critical point? So the triple point here, okay, is indicate that three different phases, which is solid, liquid, or gas, are simultaneously coexist in equilibrium. It occurs at a single definite pressure and temperature characteristic of the substance, which is not our control. So for the critical point, it is point at which the critical pressure and critical temperature of the surface will disappears. Now we are going to have a look on the definition of the boiling point, normal boiling point, critical temperature, and critical pressure. The boiling point is the temperature at which the equilibrium vapor pressure of a liquid is equals to external pressure. The normal boiling point is the temperature at which a liquid boils when the external pressure is equals to 1 atmosphere. And the critical temperature is the temperature above which the gas cannot be made to liquefy, no matter how great the applied pressure. And the critical pressure is the minimum pressure that must be applied to bring about liquefaction at the critical temperature.